Good afternoon, everyone. I welcome you all to the week 7 discussion of the course Smart Grid Basics to Advanced Technologies. So, I am Adyasha Sahoo, a PhD scholar from the Department of Electrical Engineering at IIT Roorkee. Yes, yes, sir. Sorry, I don't get you. Okay, okay. Yes, yes, it is so. You are the only one present in the meeting. That is, yes, yes. So, no worries, we'll start our discussion anyways. It's already time. Yes, I know it. What can I do regarding that? It is, okay, 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 okay. Actually, we have to complete within 4 to 6, so that is it. Okay, okay, no. So in this week, basically, we will be talking about the control of microgrids in different grid connected mode, islanded modes, and how the different control strategies are being implemented. So we'll be discussing that. So firstly, we see what is the need for the microgrid control. So the first thing is for resiliency. So this we had seen like when either in the grid connected or in the islanded modes of operation. So there will be different control strategies in these two configurations because it will in the grid connected mode you have the support of the grid. So basically the reference can come from the grid side and you can manage the microgrid operation in that way. But in the islanded mode of operation you don't have the grid support with you. So utilizing only the resources present within the microgrid, you have to manage the various attributes such as the voltage frequency of the microgrid so that they possess greater challenges than a grid connected mode. Then this energy reliability and energy efficiency, they are basically coming under this energy management system. So what is this is basically, so we had seen earlier that microgrid will be a combination of various generating resources. So there you may have a combination of such as PV, wind, and battery. So you can have other resources also. And then you have will be having a load which you need to continuously supply. So these all are intermittent resources. So depending upon the solar irradiance, depending upon the wind speed and the SOC of the battery, so there will be different operating modes of the microgrid. For example, if we consider, let's say, only we have a structure such as we have a wind energy system with a battery. So one of the mode can be, let's say, so if you are aware, so how a wind turbine basically works is basically the wind speed drives the blades of the turbine and then it is getting converted to electrical energy. So to drive the blades of the turbine, you require a minimum speed that is known as your cut-in speed. So if the speed is below the cut-in speed, then the blades cannot rotate and you cannot produce any power. Only if the speed is greater than the cut-in speed, then you can produce power from it. And similarly, you have a cutout speed. So what happens that if the wind speed is extremely high, such as in case of your cyclones or any other such high speed wind events, then it may damage the blades of the wind turbine. So what we prefer to do is, if the wind speed is very much high, so we inherently have a pitch control system where we cut out the machine, like we don't produce any power during those conditions also. So if the speed lies between this cut in and cut out speed, then only we have the energy production. So now, how to transition between this cut-in speed to cut-out speed, or all these modes? So that will require the energy management system. So what the energy management system will facilitate is, depending upon the various scenarios, its main aim is to basically maintain the voltage, the frequency of the system, and so energy management system, its objective is to maintain the system security parameters. We can say system security. Its second aim is to supply continuous power, uninterrupted power to the load, to supply continuous uninterrupted power to load. And thirdly, it also tries to basically ensure the economic operation of the microgrid. So what do you mean by economic operation is, let's say you have multiple resources with you. So to decide the dispatch schedules of the multiple resources in such way that the overall cost of energy is the lowest. So that also is done within the energy management system. So basically, to maintain the system security, to by how it will maintain the system security is basically you have various control actions, and they give the reference signals to the various converters and inverters to keep the voltage and frequency attributes within the allowable limits. And obviously, you need to ensure uninterrupted power supply to the load. And meanwhile, you also supply the power, ensuring a economic operation. So all these strategies are embedded within the energy management system in a microgrid. So these energy reliability and energy efficiency come under the energy management system. Now, grid integration. So, depending upon whether you have a DC microgrid or a AC microgrid, because we know that some or major of the renewable energy resources are DC in nature. So, we saw that we are also going towards a DC microgrid. Now, if you have a DC microgrid and it is connected to the AC main grid system, or the high voltage transmission system, then you need converters to basically transient between both this DC microgrid and the main AC system. Because what will happen in certain scenarios, when you want to inject excess power to the AC side grid, then the converter has to be a DC to AC type conversion. But when you want to import energy from the grid, in case the microgrid is not having enough power, then in that case, to import the energy from the grid, you need to have a AC to DC type of conversion. So for this grid integration, the interlinking converter is the main which does all these functions. Now, load management. So again, if it is an islanded microgrid, then it may happen that sometimes you do not have enough power to supply all the loads of the system. Then you have to basically decide which are the high priority loads and supply the energy to them first, and then you can provide power to the lesser priority loads. And similarly, if you have, let's say, uh, excess of energy with you than the load, then you can charge the battery if you have. Otherwise, you have to go for table curtailment. So all these functions, basically, you need to have control actions with you. Now, next is this renewable energy integration. So this I told you, like since they depend on the intermittent wind speed or solar irradiance or these all factors. So basically to incorporate these intermittent resources, then you need the various control strategies. Then grid support. Obviously, the microgrids can also provide various ancillary services that we discussed previously also, such as your frequency services, voltage services in the form of reactive power, or black start services, or it can provide reserves, it can provide inertia, and all these ancillary services. So for that, also you need to have control strategies with you to respond to the grid requirements. Now, energy cost management. So this will also come under the energy management system. So whatever control strategy you have fed in the energy management system, so your microgrid will function in that way to basically reduce the operating cost or basically increase the profits of the overall microgrid operation. So basically, let's say how this is done is if the microgrid, you have a microgrid and you have a main grid. So you know that the although the electricity prices, they are not constant or same throughout the day. They are time varying in nature. Electricity prices, so they fluctuate according to the changes in the load and the generation throughout the day. So let's say you have a certain this kind of electric prices throughout the day, then what your aim will be basically when you have high electric prices in this region. So during that time, the microgrid will either consume less power, consume less power, or basically import less if it is not having sufficient generation. And also during this condition, if it is having sufficient generation with that, then it will try to inject more power to the grid. Because basically in this case you are trying to sell the excess electricity at a higher prices to the main grid, and in case of this is high price. Now in case of this low price region, so this is low price region. So in this low price time periods of the day, the microgrid will try to uh, absorb power to basically charge the battery if it has, because basically it is trying to buy power at a cheaper price during this interval and sell electricity back to the main grid at higher price during this interval. Now environmental benefits, this we know, this distributed resources, they are green in energy, green energy resources. So they help in reducing the greenhouse emissions and move, help us move towards our net zero emission targets. Then scalability. So these microgrids are highly relevant in the remote or off-grid applications such as your hilly terrains and maybe for military purposes or in deserts. So where you don't have the basically transmission lines installed in those areas. So in those cases, islanded microgrid type of operation is more favorable. So how this control strategy is taking place. So you see the first thing we discuss here is a hierarchical control. So we have control strategies in various layers, taking place in various layers according to the various timescale of their operation. So the fastest control strategy layer is the local control that you can see here. So the local control is a local controller. They are the fastest layer, and the operating time is within seconds. The highlight of this control layer is in this local control layer, you do not have any communication between the devices. So it is such that, let's say, you have various resources like this here, you can see, and there are various inverters installed here, right? Like 1, 2, 3, 4, 5 inverters are there. So these 5 inverters, they are not talking to each other. Each one of the inverter will basically sense the quantity of the electric grid. It can be voltage or it can be frequency or anything. And depending upon the present grid current condition, it will act without talking to its neighboring partner. So these inverters, they inherently will have some control strategy that have been embedded within them. So it will basically sense the condition of the grid and take the action depending upon the control strategy that has been installed within it. And it is so, since it is not communicating with anything, so it is the fastest control layer and it acts within seconds. So in case of any type of disturbance, so the local controller will act first. Then after that, after the local control action, we have the secondary control layer. So in the secondary controller, here we have the acts after the local control, and here you have the communication. So here it builds upon the local controller. It builds upon the local controller to meet the global target. So the secondary control layer is aware of the grid conditions. It is having knowledge about what target you want to make, and it will take the control actions accordingly by communicating with all these inverters, and it will give signals to all these inverters to basically reach the global target of the whole microgrid. So it will act after the local controller, and its time scale of operation is from minutes, even minutes, seconds to minutes, you can say, seconds to 1 or 2 minutes. Now, finally, we have the central controller. So its time of operation is between 5 to 15 minutes. So it has two goals of the central controller. Firstly, it will communicate with the other microgrids, other neighboring microgrids, or the distribution system operator or the DNO for energy exchange in between 5 to 15 minutes. So basically, if let's say we are considering a 5 minute time scale period, so for each 5 minute, it will decide whether it has to import power or export power. Okay, and so this, let's say in the first 5 minutes, the microgrid can sense that it will have to import 5 megawatt of power. Now, for importing this 5 megawatt of power, it can request it from the distribution system operator or other microgrids or the neighboring microgrids such as this MG2 or MG3. So again, how how much quantity it will get from each microgrid or the distribution system operator will depend upon the economics. So considering the economics, it will decide what will be the dispatch schedule, basically either from the main grid or from the other resources. So that is mainly decided by the central controller. Once that is done, to manage the disturbances within these 5 minutes, you have the secondary controller and the local controller. So let's say suddenly you have a high wind speed, or suddenly you have basically change in the irradiance, then it may lead to voltage variations and frequency variations. So the first action will be taken by the local controller. If it is if the local control can manage to bring this voltage and frequency within the limit, then you do not need the secondary control action. But if the local control action is not enough to manage the fluctuations, then the secondary control layer will act upon the local control and try to bring the attributes within the limits. That is within the 5 minutes block. Now, the other operation of the central controller is in case of emergency. So, in case of your partial or complete blackouts, or the islanded or the grid connected mode of operation, distinguishing between the modes of operation. So during that time, let's say now it is in grid connected mode. Let's say it has converted to islanded mode of operation. Then the emergency controller will be triggered to manage the operations within the microgrid. And similarly, in case of a blackout also. So those actions are taken by the controller. Here also you have communications with you. Communication is required to talk with the neighboring microgrids or with the distribution system operator. So basically, in the hierarchical control, you have three control layers: the local controller, the secondary controller, and the central controller. Now, who are the basically who are responsible for the hierarchical control? So there are three major entities in this picture. So you have the microgrid operator, which is looking after the operations within the microgrid. Then you have the distribution system operator, which is looking after the operation within the distribution system. And then you have the transmission system operator looking after the transmission system. So if you see, let's say, um, um, this is a radial transmission system with thermal generators and its load. Then this transmission system is looked after by the transmission system operator. So it will look after the operation of this generators, this transmission load, and the power flow through this transmission lines, the voltages at the transmission buses. So all these come under the jurisdiction of the transmission system operator. Now, to this transmission system, you have a distribution system, various distribution system connected at the various locations. So, distribution systems are radial in nature. So it will also have various loads. It will have then DGs or distributed generators, such as your PVs. So now this is a distribution system. Similarly, you can have another distribution system connected at this bus. Here also you will have its own distribution system generator. Now within this distribution system, so this is a distribution system. This is the transmission system. Now within this distribution system, you will have your microgrids also. So let's say you have a microgrid here, you have another microgrid here. So here also. So this is the hierarchy of the connection. Now within this microgrid, you have your small distributor generations, its small local loads and everything. So the microgrid operator will look after the operation of the microgrid and the power flow in this line. This line basically the point of connection between the microgrid and the distribution system. So that will be decided by the microgrid operator whether it wants to inject into the distribution system or it wants to take power from the distribution system. These actions will be decided by the microgrid operator. For the distribution system, the power flow between the transmission system and the distribution system. So this line and this line, this connecting, this we call the boundary lines. So the power flow through the boundary lines between TS and DS is decided by the DSO. Similarly, here between the microgrid and distribution system, and finally, the transmission system will look after the operation needs in the transmission system. So this is the hierarchy of connection in the overall bulk power system, the location. So, how the local controller works? Basically, the most popular one is the group control. Within the hierarchical control, first we'll be discussing this local control layer, and within that, the technique that we will study is the droop control. So, droop is very popular. That for the thermal generators also we have seen earlier. So, the common idea here is, let's say, you have a frequency versus power curve here, and let's say initially your frequency is f naught, and this generator 1 and generator 2 are supplying power to the load. So if you see, this is f naught, the power are p1 naught and p2 naught. So p1 naught plus p2 naught is giving you, is basically power from both the generators is used to meet the load p load, and the frequency is maintained at f naught. Now let's say there is a disturbance delta P. There is a, so you see, can you tell me that if the frequency changes from F naught to F, whether there is a increase in load or decrease in load by looking at this curve? So there is a drop in frequency here, right? So frequency will drop means the load has increased. Drop in frequency implies increase in load. Now, to increase to supply the excess load, the power of the generator 1 and generator 2 has to increase. So P1 naught increases to P1 and P2 naught is increased to P2. So now P1 plus P2 is your P load plus delta P L. So delta P load is the disturbance basically. So what we need is basically this delta P1, that is increase in output of the first generator, plus delta P2, that is increase in output of the second generator, should be matched with the delta change in the load. So this we can write as delta P load. Now you see the slope of these lines are represented by this constants Kp1 and Kp2. So how we can represent this? So basically, Kp1 will be delta y upon delta x. So in the y-axis you have frequency. So f naught minus f by p1 minus p1 naught. Similarly, Kp2 is same f naught minus f, and change in power is p2 minus p2 naught. Now if this f naught minus f is constant, so we can say Kp1 times P1 minus P1 naught will be same as Kp2 times P2 minus P2 naught. So from here, this is nothing but P1 minus P1 naught is delta P1. So delta P1 by delta P2 is Kp2 by Kp1. And from this condition, we have delta P1 plus delta P2 is P load. So delta P1 equal to, so delta P load is delta P1, and in place of P2 you can write Kp1 Kp2 times delta P1, and this ratio is basically represented by the regulation constant R. So delta P load is nothing but 1 plus R times delta P1. So from here you can get delta P1 as delta P load by 1 plus R. So the increase in generator output for the generator 1 is given by this expression, and similarly substituting it, you can get a delta P2 as R by 1 plus 1. So basically, if you have this increase or decrease in the load quantity, and you know this regulation constant R, you can calculate how much power is being shared by the generators, generator 1 and generator 2. Now, what is the problem with this droop control? So for this droop control is basically uh, it works for load sharing, but it does not work accurately for voltage regulation. So what will happen is basically in case of disturbances, external disturbances, you cannot regulate the voltages using this group control in an effective manner. What happens mostly is basically the voltage will fall below the limits or above, go beyond the upper limit, and hence it may damage the equipment. Now, secondly is voltage and frequency droop. So basically in the droop, you are having both the voltage and frequency with you. Now, since both of them are closely related, so although it helps in good load sharing, but due to the effect of voltage and frequency on each other simultaneously, it is very difficult to basically tune the droop coefficient R, because what you need to also control the voltage, you need to also control the frequency. So tuning of this R becomes a challenge, because once if you're trying to set the frequency, it may lead to poor voltage regulation. But if you are going for good basically power sharing or frequency regulation, then it hampers with the voltage regulation. That we'll see in the curves also. So due to this tuning of the R is difficult for this. Similarly, limited capacity for reactive power. So this we will see what happens in due to the reactive power control using the droop methods. So various phenomena of we have seen hunting or other issues that we'll see through the curves that also are taking place, due to which again you need additional power control mechanisms. Only droop cannot work. You need other devices to work in coherence with the droop control to manage the voltage of the system. Now, synchronization challenge. So basically, since you do not have the generators with same ratings or same make within the system, different generators have different sizes, different types. So basically, matching this group coefficient R to ensure the proper voltage regulation or frequency regulation, that is also a challenge. So the improved droop methods, what you do to basically build upon the droop methods. So using this virtual impedance method, so there we try to include the effect of the lines that is being connected. Then you have adaptive droop control. So you saw that the vanilla droop control method or pure droop control is something like this, where you have a decreasing slope, basically a line with such characteristics. So what we do in adaptive drift control is we change these characteristics. So basically, if in the context of reactive power and voltage, we say we change this characteristic to something like, say, this way or this way. So depending upon the application, you can change this droop characteristics. So let's say this is Q, this is V. So this is the Q max, and this is minus times Q max. And let's say this is 1 per unit. So what we want is, instead of earlier the voltage QV curve, if you see, so this was 1. So if the voltage is greater than 1, so what we need, we, okay, earlier it was like this way. So even if there is a slight increase in voltage from 1.0 to 1 point, let's say here it voltage increase to 1.003, then also the loop will work. But it is difficult to maintain dot point one at all times. So what we did is we modified it so that if the voltage is, let's say, between 0.98 to 1.02, so within this band, this we say that it is also acceptable voltage range. We do not want the droop controller to act, so we do not inject or absorb any Q from the system. So hence the droop control is ideal within this voltage band. But if the voltage increases beyond 1.02, that is this region, or if the voltage drops below 0.98, that is this region, till 0.95. This is 0.95. This is 1.05. So in this region, we inject or absorb the Q proportionally, because you see this is the straight line. And once if the voltage goes beyond 1.05, this region, or the voltage drops below 0.95, then we are giving, that is the alarming condition, because we don't want the voltage to go beyond those ranges. So we give full support, that is we inject maximum Qmax or absorb maximum Qmax to the system to give full support during those voltage conditions where there is extreme drop or rise in the voltage. So that way we basically change this vanilla droop control method to this adaptive droop method. So similarly, angle droop means here you have P and V basically. Now virtual frame transformation. So here basically we convert the phases ABC quantities to their direct DQ axis frame, direct and quadrature axis frames. Or basically it helps in simpler calculations and understanding. Then virtual inertia based droop control. Now, what is this virtual inertia? Is basically this inverter-based resources, DERs that we say, they do not have enough inertia with them. So what will happen is even with the smallest amount of power fluctuations, the frequency or the frequency will change drastically because they don't have any inertia with them, unlike our large thermal generators. So we have this virtual inertia concept that we basically try to mimic the inertia features or the characteristics of inertia using a controller, so that if the voltage so that basically if the power mismatch is very small, then this controller will act and stabilize the frequency. It will not let the frequency to shoot up or go down. Now we have then the secondary control layer. So in the secondary control layer, as we discussed, it will build upon the local controller, and it time scale of operation is after the local controller. So its time scale is after the local controller, and here you have communication with you. So the main objective of here of the secondary controller is to basically for the optimal dispatch of the distributed energy resources. So this is the first operation. And the second is restoring the voltage and frequency after the primary control. So basically, let's say your voltage went down, and now the system voltage was somewhat around 0.92. So immediately what will happen? Your local controller will act, and the local controller was able to improve this voltage, and the voltage was now, let's say, 0.935 after the action of the local controller. Now the voltage is 0.935. So now the secondary controller will act. Secondary controller act, and it will try to further improve the voltage and bring it to, let's say, 0.95 or 0.96. Basically anything greater than 0.95. So that will be done by the secondary controller. Now for this, you need to basically have the real-time optimization. So you need to build a optimization model, which that and the objective of that optimization model will either be to minimize the overall losses, or to minimize the operating cost, or to minimize the voltage fluctuations, or minimize the frequency fluctuations, depending upon what objective or what application you want to work for. Then you have a set of constraints, and you solve this optimization problem to get the dispatch schedules of the various distributed energy resources with you. So economic dispatch and unit commitment. Now, if it is an islanded microgrid, so the secondary control layer is the highest hierarchy. Only if you have a grid connected mode, then you have the central controller with you, because the central controller was communicating with other microgrids or the DSO. So if it is the islanded microgrid, then the secondary control you have only two control layers in case of this islanded microgrid conditions. So islanded microgrids will have two control layers, primary and secondary. So this operates in a so this control operates in a slower time frame than primary control, because obviously after primary control layer, then only we have the action of the secondary controller. Now the secondary control layer can be centralized or distributed. We'll see how what are the distributed methods here, how it our operation is taking place. And lastly, the secondary controllers are not necessary to be frequently operated, hence our event-triggered approaches. So what it means that here we saw that after the local control layer, the voltage was not within the acceptable limits, so you needed a secondary control layer. But let's say if the voltage was at 0.92 and with the local control action, now the system voltage was improved to 0.95. So now the voltage is within the limit. So you do not, no secondary control action is required, because only the local control action was enough to bring the system back to your acceptable limits. So hence the secondary control layer will not always be operated, will not always be operated. Only triggered. What is this event triggered? That after this local control, if there is need for the secondary control, then only we trigger the secondary control actions to take place. Now, lastly, we have the central controller. So it is the highest and the lowest level of control for grid connected microgrids operating in hierarchical control schemes. It is the highest. So it monitors the micro, local, and secondary controllers. So let's say if you have such a condition that even after the operation of the central controller, your system is not back to its normal operating condition, then you need the help either from the distribution system operator, that is your upper level grid, or you need to take help from the neighboring microgrids. And that you do with the help of that communication basically takes place using the central controller. And it is also so it sets the long-term set points for the DR units. So as I had said, for 5 minutes, the DR set points are set by the central controller. Now, for within 5 minutes, the DR set points are set by the secondary controller, and within seconds, you have the local control. Now, it is responsible for managing multiple microgrids that we also see. We have discussed that we can communicate with the neighboring microgrids, and for that, we need the central controller. And similarly, this control level is also responsible for managing the operation between the microgrid and the main grid or the distribution system. So if you see here, so this microgrid MG2, it can either take help from MG1 or MG3, or it can take help from the distribution system. So here you see this MGCC1. So through the central controller, it can communicate with the DNO or the other microgrids. For that, you need the central controller. It is also responsible for islanding detection and also the emergency control and overall protection schemes. So, in case of faults, in case of blackouts, in case of islanding of the microgrid, for all this, for managing all these operations, you need the central controller. So, we will see the distributed control strategies. What are the different types? So, for before that, we'll discuss what is the centralized approach. So, what happens in the centralized approach is you have the central controller here with you. Now, let's say you have microgrids, multiple microgrids. So, each microgrid will first communicate with the central controller. So, let's say MG2 is telling that it needs to buy 5 megawatt of power from the main grid. MG1 tells it needs to buy 3 megawatt of power from MG4. MG4 tells that it can sell, let's say, 5 megawatt of power, and MG3 is telling it can sell 4 megawatt of power. Like this, they will give their requirement to the central controller, whether they are in deficit of power or whether they have excess amount of power with them. After that, what the central controller will do, it will solve the optimization problem to decide the dispatch schedule for all these microgrids, considering the economics to basically minimize the overall operation cost. And once the dispatches have been decided, it will give back those information to all the microgrids. And then the microgrids can again function. That is for the 5 minute time window. Now, what are the disadvantages of this method is firstly, so it will lead to first is single point of communication failure. So what this single point of communication failure means, because every action is being decided by the central controller at the upper level. Now let's say communication failure happens and the central controller is unable to communicate with the microgrids, then these microgrids they are in dark, like they don't know what to do, like what action they need to do. So communication is it secondly we can say it has having high communicational burden, because first it needs to collect information from all the microgrids and then it does also convey those messages back to all the microgrids. So the number or the rounds of communication is high in the centralized approach, and if there is a communication failure, then everything will go wrong. You do not have any backup plan for this. So to reduce this communication burden and the dependency on the communication rounds, the first thing that we have is this multi-agent based techniques. So here what you do is basically, So instead of basically communicating to the central station, they will communicate with their neighbors. So MG1 will communicate with MG2 and MG4. MG3 will communicate with MG4 and MG2. MG2 will communicate with MG1 and MG3. And what is left? MG4. MG4 will communicate with MG3 and MG1. So each microgrid will communicate with its neighbor and take the actions basically. So this type of structure we call as peer-to-peer communication, or P2P. So since there is communication between them, so they can, by communicating with each other, they can be able to meet the global target. So here communication burden is lesser than centralized. Although since it is for a smaller system, the communication burden effect is not that evident here. But if you go for a very large, complicated system with very large number of microgrids, then the number of communication rounds required in a P2P communication is less than the number of communication rounds required in the centralized approach. So without the need of a global controller, they can communicate with their neighbors to meet the overall global targets. Now, the next type of technique is your model predictive control technique. So, what we do here is basically we adaptively change our plan to meet the global targets. So, in the model predictive control techniques, what we do is basically at t equal to 0, that is your initial condition. So, you neither know the state of the system, initial x, and at let's say t equal to 5, you need the final state xf. Then to reach from this x naught to xf, what action you need to take, that is represented by u. So at t equal to 1, t equal to 2, t equal to 3, t equal to 4. So you divide the time interval from the initial to the final with certain blocks that I said, like from T1, 1 to 2, 2 to 3, 3 to 4. And at basically, you are taking the control actions in steps. So that depends that you can change this control action steps. So let's say we are taking 4 control steps, and uh, this control actions are represented by U. So these are represented by U. So what the optimization model or the model predictive controller will do It will analyze your initial condition X naught. It will take into consideration the final state XF or the global target that you have to reach. And it will give you the plan that what control action you need to take at T1, T2, T3, and T4 to reach from X naught to XF. So it will give you U1, U2, U3, U4 at T equal to 4, T equal to 3, T equal to 2, at T equal to 1. Now, let's say you, if I give the example, let's say from, uh, let's say you have an exam tomorrow. Okay. Let's say you have an exam in 5 hours. So your initial state of knowledge is, let's say, X naught, and your final state is XF. So let's say you have five uh, chapters to complete. So initially you have not read anything X0. Your final target is to read all the 5 chapters, and you have, let's say, 5 hours with you, 4 hours with you, let's say. So what will be your initial control action is that in each hour I have to complete one chapter each. So let us make this 6 and let us make this 5. Okay. So let's say you are starting from here and you want to go till here. Okay, from 0 chapters to 5 chapters. So the plan is simple. Each hour you need to read one chapter. Now let's say in the first chapter, after uh, taking up the first chapter at t equal to 2, after like, so this was at t equal to 0. Now you are at t equal to 1. So according to your plan, you should complete chapter 1 after 1 hour, right? But now when you see the after 1 hour, you have not completed chapter 1. You are still in the middle of chapter 1. That means your plan has not gone according what you had, like things have not gone like what you had planned. So now you have to change the plans. So now it is that at t equal to 1, you have to go from some x naught dash to xf, and then but the time has reduced. Now you have only 4 intervals with you. Now to complete same 5 chapters, you don't have 5 hours, you have 4 hours. That means you need to cover more than one chapter in each interval. So you then re-evaluate your plan, and the new plan is such that, so this is your revised plan to reach this XF. XF is 10 to complete the 5 chapters. Similarly, at at t equal to 2, you again re-evaluate what is your progress and what is your target, and basically for the next 3 intervals you again plan and you have new control actions with you that you have to take. Similarly, this will go till your fifth time interval. Now in case of power system, let's say your voltage was at point 82, you want to go to 0.95. Now after t equal to 1, now the voltage has improved from 0.82 to point, रुको, 0.824813581447. Okay. Let's say the voltage is now at 0.86. So now you recalculate to reach that voltage at 0.95. And at then you reevaluate at t equal to 2, let the voltage has improved till 0.9, then you reevaluate. Let's say now again it is at 0.93, then you reevaluate and so on. But your final is always fixed. So is this clear? I don't know how clear it was. You can like interrupt me. Okay, we'll move to the next type of control technique, distributed control technique. That is your consensus-based approach. So the major issue in this communication-based control techniques, because this is secondary means you have communication with you, you need to communicate with the others. Now, communication is nothing but passing of information. So this brings us to the concerns of privacy. So because all these power, dispatch, buying, selling involves a huge amount of money and security concerns also. So communicating, everyone may not be comfortable for sharing their power data, their load data, their characteristics. So they may not want to share with the others. But still, the system you need to go towards the global target. So let's say like earlier, you had four microgrids. So one, two, three, and four. So here, it had to share its power P2 with both. This has to share P3 with both, and similarly P4 has to share with both, and P1 has to share its required power. Now, what is happening is P2, it knows about its power requirement, it knows about P1, it knows about P3. So in the future, it can basically manipulate this power, and it can hamper the operation. If it wants, it can hamper the operation of P1 and P3. Similarly, P4 has the information of P1 and P3 with it. So this sensitive information can be manipulated by them to hamper each other. So what in consensus-based technique we do is, instead of sharing these powers, so we communicate instead of communicating P1, P2, P3, P4. We can communicate either, we can scale these powers like K times P1 or K1 times P1, K2 times P2. So instead of telling the true powers, you can scale these powers. Or what you can do, you can also communicate something like average of the powers, like P1 plus P2 plus P3 plus P4 by 4, or difference between the powers. So instead of giving the powers directly, you can do some operations with the information and then pass it. Then the by doing so, basically, no one has the exact idea of what exact power requirement is because you have basically manipulated these powers. But by manipulating this information, the concern or the care that you need to take is with this information, the secondary control should be able to reach the global targets. Otherwise, there is no point of privacy if you are not able to meet the global target. So by basically instead of communicating P1, P2, P3, P4, you can communicate any masked data. You can uh, basically do some operations on this data for sharing on information between the microgrids. But by changing this data, information that is shared, still you need to reach to the global target. That that your formulation should be in such a way. So that is the consensus based control techniques. Now, what are the types of DC microgrid control? So decentralized control, this we saw, this is the local control, no communication. And this is the fastest one. Next, in the distributed control, that is the secondary control, right? Secondary control layer. There you have the communication, and your main target is basically build upon the local control to manage the operation of the system and also decide the schedule for the economics point of view. It will act after the local control. And in the secondary control, centralized control or the tertiary control layer, so it will communicate with other neighboring microgrids or the distribution system operator in case of to basically decide the dispatch schedules for the economic operation. Also, it will take actions in case of fault, in case of islanded condition, and other emergency control actions will be done by the centralized control layer. So we have various advanced group control techniques such as your virtual resistance, adaptive group control, intelligent based. Basically, we try to modify the group characteristics for better performance and mode adaptive group control. So, what is this mode adaptive group control? Basically, you have three modes of operation. In the mode one, the in the mode one, the is in utility is in the group control mode, and others are in the constant power mode. In the mode two, the energy storage is in the group mode, and the other are in constant power mode. In mode three, the DG are in the group mode. Now, again, there are various types of decentralized control techniques, such as your voltage leveling technique. So here we are talking about DC. So the quantity with you is P and V. The voltage leveling has certain disadvantages for large scale operation of basically for larger systems. So for that, then we move towards the DC bus signaling method, then the power line signaling method using communication techniques. Then you have various types of distributed control. So what happens in so remember again, it is decentralized control means there is no direct communication here. In the distributed control, basically the types are depending upon what information are you sharing in the distributed control. So if you are sharing something as average of the current, it is the digital average current sharing method. In the average voltage sharing method, you are sharing the information of average voltage within the microgrids and the distribution system. Or in the distributed cooperative control, you are basically considering other information that is being communicated. So depending upon what information you are communicating, this is the various types of control techniques available. Now we have the type of operation for DC microgrid. So we know that either they can be in the grid connected mode or they can be in the islanded mode. So if you have a grid connected microgrid, then the resources, or let's say PV that you have with you, it can always generate in the MPPT mode, because if your PG becomes greater than PD, you can inject this power back to the grid. So you can always operate in the MPPT mode to avoid any curtailment of your green resources. But in the islanded mode of operation, there is certain challenges. So it will depend again whether you are having a battery with you or not. And again, if you have a battery, it will depend upon the SOC of the battery, whether you will go for load curtailment or renewable curtailment or something like that, depending upon the case studies. So let's say you have islanded microgrid with a battery. So let's say in case one, the SOC of the battery is zero point 0.1, then can the resource operate in MPPT mode? Will the renewables operate in MPPT mode? You are aware of the MPPT mode, right? A maximum power point tracking. Basically, you try to derive the maximum power from the resource using this technique. So obviously you can operate in NPPT mode because your battery SOC is zero point 0.1. So if currently if your PG is greater than PD, you can charge your batteries. You can charge your BESS. But if PG is less than PD and your SOC is not enough to meet the load, then you have to go for load curtailment here because you do not have enough power with you. Now in the case 2, let's say your SOC is zero point 0.9, then can you operate in MPPT mode? So here, if your PG is greater than PD, you cannot charge your base. It is already at zero point 0.9 SOC. So what you have to do, you have to curtail your renewable. So MPPT mode of operation is not possible. But if your load is greater than generation, you can discharge your base to meet the load. So no MPPT in this case. This case you can have MPPT. This case you can have MPPT. Yes. And here also you can have your MPPT. So depending upon the SOC of the battery, the operation of the microgrid will, yes, Devanshu, you want to ask something? Okay. So depending upon the SOC of your battery, it will depend whether you can operate in the MPPT mode of operation or not in case of your islanded microgrids. But in the grid connected mode, you can always operate in the MPPT mode. Now, what is the typical structure of a DC microgrid? So, basically, this is the main grid, and then you have this is AC. So you have a grid side converter, JST grid side converter, which is converting this AC power to DC. But then again, it will all not always be AC to DC since you have bidirectional power flow. We'll discuss that later. First, see the architecture here. So you have PV with you. This is a DC microgrid. So this is a DC bus. So to integrate this PV with the DC bus, you have a DC-DC boost converter, which basically will increase the voltage level, boost up the voltage from PV to the DC bus. Then you have a hybrid storage system. So we know that for hybrid storage system, we take one with high energy density. So battery is high energy density, ultra capacitor is high power density. We combine them to form a hybrid energy storage system. Now, these are then integrated with the bidirectional converter, DC converter. Then if you have a wind is AC source, so you have a AC-DC converter, and then followed by that you boost the voltage using DC-DC converter. So everything then is DC here, and then you have the DC loads here. Now let's say this grid side converter. So if we in the DC microgrid, your uh, let's say microgrid has to inject power to main grid, then what is the action of the grid side converter? So if you want to inject to the grid, so this is your utility, this is your microgrid, this is the boundary line connecting them, this is DC, this is AC. You want the power to flow in this direction. So what is the type of converter that you need to have converter action? You need DC to AC conversion, right? So this grid side converter has DC to AC conversion. Now, if microgrid has to absorb power from main grid, so power heads in this direction. So AC to DC conversion. So depending upon the direction of the power flow in the boundary line, the grid side converter has to function accordingly. Now, this was a pure DC microgrid. Now coming to a AC DC microgrid. So here you have combination of both AC and DC resources. So you have DC generation, you have AC generation, you have storage with bidirectional. Similarly, you have AC generation and DC generation here also, and you have a storage. Now the key difference is here you have both AC load and a DC load. So for that, earlier you had only one DC bus here. Now in a AC-DC microgrid, you need one DC bus and one AC bus. So this is the DC bus, this is the AC bus. So for DC bus, everything that is being integrated, like all this power that is coming here, has to be DC. Similarly, for connecting with the AC bus, everything is needed to be converted to AC. So now between this DC bus and AC bus, you have this interlinking converter, and again, its operation will depend upon the power sharing between these microgrids. Now in the configuration 2, what you have is you have a pure DC microgrid here with a DC bus, and you have a pure AC microgrid here with a AC bus, and you have an interlinking converter. So what is the difference between these two configuration is, in this you had a mixture of both AC and DC in microgrid 1, and here also you had both AC and DC in microgrid 2. So you needed a huge number of converters here, you see. But if you have a pure AC microgrid, here all resources are AC and here all resources are DC. Then you have a pure DC bus, pure AC bus, so the number of converters required is drastically reduced. Now again for the operating, we have various operating modes for AC-DC microgrid. We will see that in the grid connected mode, either it can be in the dispatched power mode or in the undispatched power mode. So we'll see here what happens in each mode. So coming to the first, in the dispatched power mode, the interlinking converter ILC is working on the DC voltage regulation mode. So here ILC is in voltage regulation mode. That means it sets the voltage of the DC bus, and all other resources will follow this set point of the DC bus. But in the second mode of operation, the DGs are in the voltage regulation mode. That means they are controlling the voltage of the reference bus, and other devices, the interlinking converters and other storages, they will basically uh, follow this voltage and give the output power. So here ILC will be in power mode, and DGs are in voltage control mode. Here ILC is in voltage regulation mode and DGs are in the power. So this is the dispatch power mode. In the undispatched power mode is basically all the DGs are not controlling their output power. They are always working on the MPPT because this is the grid connected mode, so they can always work in the MPPT mode, right? And the storages, they are basically charged or discharged depending upon whether you want power to be injected or you want power to be fed to the loads. And the function of the interlinking converter is basically to regulate the voltage of the buses. So here basically you're not controlling the power of the DGs, right? It is a undispatched power mode. That's why you're not dispatching them. Just whatever they are providing, you are using it and you're injecting it into the grid or charging your batteries with it. Now, in case of your island, so this was in the grid connected mode. In the grid connected mode, you have either dispatch power mode or undispatched power mode. Now, coming to the standalone mode. So, in the standalone mode, the interlinking converter, your ILC, is in voltage regulation or voltage control mode of the AC side. And controlling the AC one of the side means that other side will be indirectly also controlled by the ILC. So, and this can be again divided into direct DC link voltage mode or indirect DC link voltage control mode. So, in the direct voltage control mode, the DGs and the storage, they are detecting the voltage of the DC link. So here it is fixed that ILC will control the AC side. In the direct DC link voltage mode, the DG will regulate the DC link voltage, and in the indirect DC link voltage, the basically mismatch, power matching will detect the voltage of the DC. You're not directly controlling the voltage here, depending upon whether you are matching the if how you are matching the generation with the demand, that will detect the voltage at the DC bus. So here also you can have parallel operation of the ILCs. Here basically AC is controlled by ILC and DC you have direct, indirect. Okay. This is for standalone operation. Now, then switching from the grid connected to the standalone operation or the islanded mode of operation, how that is done. So the switching from we are going from grid connected to island. So the DGs, they are converted from current control mode to voltage control mode. That is the operation of the DG. And similarly, this switching has to be applied to all the converters and the interlocking converters. Now, how to basically convert this DG from the current control mode to voltage control mode? So that is being recently studied extensively here. So some for basically faster transition. So how without reducing the DG line current to zero, you can convert it from current control mode to voltage control mode, and all these are being carried out. Then the islanding detection algorithm is used to determine the disconnecting time instance. Basically, that what time basically you need to have this transition, the switching transition that is decided in this algorithm. Now, how the power management is done, then this is only the switching operation, how the switching operation is taking place, that we discussed here. Now how the power management will take place when you are going from grid connected to the standalone mode. So the smaller DG will stay in the MPPT mode. They will inject the maximum power that they are generating, the smaller DGs, but the larger DGs and the storage, they will coordinate in such a way that the voltage is maintained. Now, power sharing among DGs during transients. So basically, transient is from grid connected to the islanded mode of operation. So for that, you can do your troop control, modified troop control, or adaptive troop control. So that basically this power sharing that we decided, no, like this power sharing. So how the power will be shared among the DGs that can be decided using various types of troop control methods. Now then passive synchronization and active synchronization. So in passive synchronization is nothing but manual operation. So what you do, you basically are monitoring the voltage at voltage between the grid microgrid voltage and the grid voltage, and you match the voltage magnitude and the voltage phase angle. Like whenever you see that they are same, you are going for the synchronization. So this is easy and practical, but since you are doing manually the matching, it may sometimes lead to transients also, right? Because it will not be exactly like whenever you synchronize, the voltages will not be exactly same. There might be some differences, and these difference in voltage may lead to circulating currents in the passive synchronization technique. Now, in the active synchronization technique, what you do is basically one of the converters or the DG will act as the what we had seen that the grid forming mode that we had seen, no? So it will set the set point of the voltage and other grids will follow it. And so one with the of the DG will initiate and other DGs will follow them. So now we will discuss some question Q&A session. The first question here is large droop coefficient in the DC microgrid leads to less voltage deviation, large difference in current sharing, larger voltage deviation, or none of this. What will be the answer here? Mm, it will be, mm, So here 2 has greater or larger to coefficient than 1. So we'll see that for a constant power, what is the change in the voltage deviation? So if you see here, this is V2, this is V1. So this is delta V1, this is delta V2. So the one with larger droop, basically 2, is having here delta V2 is greater than delta V1. So it is having larger voltage deviation. In the mode 2 of the adaptive droop control method, so the energy storage device and the DGs will operate in which mode? Constant power mode. Like both will operate in both the energy storage and DG will operate in constant power mode, or energy storage will be in droop mode and DGs will be in constant power mode, or vice versa, or both of them will be in constant current mode. So in mode 2 here, this was the mode 2. So energy storage is in droop mode and DGs will be in constant power mode. So energy storage in droop control mode, DGs in constant power mode. What is the main objective of the grid voltage source converter in the DC microgrid? To regulate the DC grid voltage, active power balance within the DC microgrid, or both? So it is both, right? It regulates the DC voltage and it is also responsible for the active power balance because basically the voltage and the active power balance are closely related in the DC microgrid. So it is both A and B. Now AC DC microgrids are connected through interlinking converter, cycloconverter, DC DC converter, or all of the above. It is interlinking converter, right? ILC. We discussed that and its operation also. Which has the fastest time scale of operation? Local control, secondary control, central emergency control, or none of the above. Fastest is actually local one. It is in seconds. After that, you have secondary control in 1 to 2 minutes, and this is in 5 to 15 minutes. So it is local control. Which of the following do not rely on any communication for their operation? Decentralized control, distributed control, or centralized control, which has no communication. It is decentralized control, right? That's why it is the fastest because it is not communicating with anyone. In the distributed control, you have communication, and depending upon that, we saw, depending upon the type of communication, consensus based or multi agent type, P2P type. And centralized control is used for communication with the neighboring microgrids and with the DSO. So, communication between microgrids or DSO, communication within the microgrid. Here, there is no communication. Next is the disadvantages of centralized control schemes are a single point of communication failure, high communication burden, or both A and B. None of this. Yes, it is both A and B that we have seen. because you have only the central station taking the action. So if there is failure of that station, then you don't have any action to take place. And due to that, you also have high computational burden on the system. What is the disadvantage of the passive synchronization scheme? Difficult for practical application, may lead to circulating current, require close coordination and communication, or none of these. So in the passive technique, basically you are manually monitoring the voltages, you are manually matching the voltage magnitude and frequent phases, and you are synchronizing it. So although it is easy and it does not require communication, but it may lead to circulating currents because in the manual operation, you may not exactly match the voltages, which may lead to, and this differences in voltage may lead to circulating currents. The power management strategies are challenged under different loading conditions due to the presence of constant power loads, voltage dependent loads, frequency dependent loads, or all of the above. Yes, it is due to the presence of all these type of loads due to the various characteristics, composite characteristics of various loads. Now, what do you mean by a 7% drop in local hierarchical control? 7% deviation in frequency, 100% change in output power, 7% in power, 100% in frequency, or the vice versa here. Yes, one is correct, and similarly, another one option is also correct among 3 and 4. One is correct among 3 and 4, which is correct. C is also correct, right? A 70% deviation in frequency will give 1000% change in output power. Which one is the type of advanced droop control technique? Power line signaling, voltage leveling, droop control, virtual resistance based droop control. It is asking a type of droop control technique. Yes, it is virtual resistance based droop control. Which of the following is correct? A hybrid storage system combines a battery with its energy management system and ultra capacitors. The ultra capacitor is a low energy and high power density device. Which of the statement is correct? So hybrid storage will combine battery technology with high energy density and high power density. So this is requires a high energy density type technology. Ultra capacitors are high power density type technology, storage technology to form a hybrid storage system. So this is correct. This is also correct. So both. Which of the following is not true in case of global hierarchical control? It facilitates an economical optimal operation, slowest control in hierarchy. It is decentralized control. Global control manages power flow between microgrids and others. It is asking about your tertiary control or the central controller. It manages the power flow between microgrids and others. It communicates with microgrids and DSO. This is true. It is asking which is not true. It also facilitates economic operation. So its main task is to decide the dispatch schedules for DRs for their economic operation. It is also the slowest control in hierarchy, 5 to 15 minutes. It is not a decentralized control, no, it is a tertiary control or a central controller. Decentralized control is your local control layer, the fastest one. So this is not true. Which of the following is a type of intelligent control technique? Virtual impedance, angle group, multi-agent based, or all of the above? Actually, these are type of group control methods to improve the performance of group. Multi-agent based controller is an intelligent control technique. If you have any doubts, we can discuss for this week or previous weeks. Okay. So yes, I'll just tell. Because the time of time scale of operation, for that we are telling it as layers. I'll just where is that slide? Yes. So the local control layer that we say, so that is for each of the inverter. So this inverter is a local control. This all this they will not communicate with each other and they will operate first in within seconds. After they operate, so this is one layer of control. Like as I said, let's say the voltage is at 0.82. So the first control layer is the local control layer, which will try to improve the voltage. And let's say it is able to bring the voltage to 0.86. After that, the secondary control layer will act. So the secondary controller will act and then it will further try to improve the voltage and it will try to bring it to, let's say, what is the acceptable point 9 or 9.5. So that work of the secondary controller is to build up upon the local controller and to manage the fluctuations within the system. And above all this, you have the central controller. So let's say if this was also not secondary control layer brings it, let's say, to 0.92, then above that you have the central controller. So it will come. So going to the central controller means you cannot manage the voltage within the microgrid. Now you have to take the help from either the neighboring microgrid or the distribution system, and that will be done by the central control layer to bring the system back to your acceptable voltage of 0.95 or something like that. Yes, sir. Model predictive control. Yes, yes. Oh, modal and modal analysis. So this is model, not the modal analysis. Yes, sir. Yes, sir. That is from the stability and that right to left eigenvectors, that all thing. Thank you. Thank you, sir. Okay, then I think we can wrap the discussion for this week. We can meet in the next week, same time, for discussing the contents for week 8. Thank you for joining.